Welcome to the discussion. Today we're diving deep into the paper VILA-U, a unified foundation model integrating visual understanding and generation. This research proposes a unified framework for visual language tasks, eliminating the need for separate modules for understanding and generation. Let's start with the core innovation. What problem does VILA-U solve, and how does its approach differ from existing methods?
VILA-U addresses the inherent misalignment and complexity arising from using separate modules in traditional visual language models, VLMs. These models often employ distinct components for understanding, e.g., feature extraction, and generation, e.g., diffusion models, leading to inefficiencies and suboptimal performance. VILA-U, in contrast, uses a single autoregressive next token prediction framework for both tasks, streamlining the architecture and improving performance.
The paper highlights a unified vision tower. Can you elaborate on its architecture and the role it plays in achieving this unification? What are the key design choices that make it effective?
The unified vision tower is crucial. It converts visual inputs into discrete tokens via vector quantization, VQ, a process that's often problematic in VLMs due to a loss of information. To mitigate this, VILA-U incorporates a contrastive learning objective during pre-training, aligning these discrete visual tokens with textual inputs. This alignment is key to maintaining strong visual perception capabilities, even with the discrete representation. The use of residual quantization further enhances the representation capacity without significantly increasing computational cost.
The paper mentions different training recipes. Why is the chosen recipe superior to others? What were the challenges encountered during the development of the training process?
Simply combining contrastive and reconstruction losses during vision tower training proved unstable. The conflicting goals of high-level semantic understanding, contrastive loss, and low-level image reconstruction loss hindered convergence. The successful recipe involves a staged approach. First, aligning the vision tower with text using pre-trained clip weights, freezing the text encoder, then adding reconstruction loss while maintaining alignment. This leverages pre-trained high-level semantic priors, enabling efficient learning of both high-level and low-level features. Other recipes failed due to the lack of pre-trained weights, inability to learn low-level features, or instability caused by training the text encoder simultaneously.
The choice of residual vector quantization, RQ, is interesting. How does this technique contribute to the model's performance, and what are its advantages over standard VQ methods?
RQ allows for a finer approximation of the visual features compared to standard VQ. By recursively quantizing the residual error at multiple depths, RQ effectively increases the representation capacity of the discrete tokens. This is crucial for both understanding and generation. The advantage is that the LLM only needs to predict code embeddings, with a depth transformer autoregressively predicting the code's H depth, keeping the computational cost manageable.
The multimodal pre-training process is described as unified. Can you detail the different data forms used and the rationale behind the training objective? Why were certain data combinations excluded?
The pre-training uses various text, image, and text video concatenations. Image, text, text, image, text, video. Supervision is applied to the latter modality in each pair to encourage modality alignment and avoid unconditional generation. An interleaved form is used for enhanced understanding. The video text form was excluded during pre-training for efficiency, but its inclusion during fine-tuning proved effective for video understanding. The unified training objective is the standard next token prediction, adapted slightly for the depth-stacked structure of RQ visual tokens using a depth transformer.
The results show VILA-U achieves near state-of-the-art performance on various benchmarks. However, the paper also acknowledges limitations. What are the key areas where VILA-U could be improved in future work?
While VILA-U demonstrates strong performance, there's still a gap in visual understanding compared to models using continuous visual features. Visual generation quality also lags behind state-of-the-art diffusion models. Future work should focus on bridging these gaps, potentially through architectural improvements, larger data sets, or exploring alternative quantization techniques. Further investigation into the interplay between contrastive loss and reconstruction loss during training could also yield improvements.
The ablation studies provide valuable insights. Can you summarize the key findings regarding the impact of contrastive loss on both visual understanding and generation?
The ablation studies clearly demonstrate the crucial role of contrastive loss in visual understanding. Removing it significantly reduces performance on various benchmarks, highlighting the importance of text-image alignment. In visual generation, while the contrastive loss slightly decreased FID scores, likely due to a trade-off with reconstruction quality, it still contributed to the overall performance, demonstrating the value of the unified training approach.
The paper mentions the use of classifier-free guidance, CFG, during visual generation. What is the effect of varying the CFG value, and what is the optimal setting found in the experiments?
CFG helps control the balance between image quality and adherence to the text prompt. The experiments showed that a CFG value of 3.0 yielded the best FID score on the MJHQ 30K benchmark, indicating an optimal balance between these two factors.
Looking at the qualitative results, what are some of the most impressive capabilities demonstrated by VILA-U? Are there any specific examples that highlight its strengths?
VILA-U's ability to perform diverse tasks, including detailed video captioning, accurate visual question answering, and multi-image reasoning, is impressive. The examples in the paper showcase its capacity for in-context learning and generating high-quality images and videos, even with a relatively small training dataset. These qualitative results support the quantitative findings, demonstrating the model's versatility and effectiveness.
The paper concludes by mentioning the potential of VILA-U as a general-purpose framework. What are some potential applications and future research directions that you foresee for this type of unified model?
VILA-U's unified architecture makes it suitable for a wide range of applications, including image and video captioning, visual question answering, image and video generation, and multimodal chatbots. Future research could explore scaling the model to even larger sizes, incorporating additional modalities, e.g., audio, and developing more sophisticated training techniques to further improve performance and efficiency. Investigating the model's robustness and addressing potential biases are also important considerations.
The paper discusses the use of LL-27B as the base language model. How crucial is the choice of the base LLM to the overall performance of VILA-U? Could other LLMs be used, and what would be the implications?
The choice of base LLM is significant, as it provides the foundational language understanding capabilities. While LL-27B was used in this work, other LLMs could potentially be used, but their performance might vary depending on their size, training data, and architectural differences. Larger and more powerful LLMs might lead to better performance, but would also increase computational costs. The compatibility of the LLM with the Vision Tower's output representation is also a critical factor.
The datasets used for training are mentioned. How important is the quality and size of the training data to the success of VILA-U? What are the trade-offs between using a larger dataset versus a smaller, higher quality dataset?
Both the quality and size of the training data are crucial. A larger dataset provides more diverse examples for the model to learn from, but the quality of the data is equally important. Noisy or inconsistent data can negatively impact performance. VILA-U's success demonstrates that a smaller, high-quality dataset can be effective, especially when combined with a well-designed training strategy. However, scaling to larger, high-quality datasets would likely further improve performance.
Finally, what are the key takeaways from this research for the broader VLM community? What are the most significant contributions of VILA-U?
VILA-U's main contribution is demonstrating the feasibility and effectiveness of a unified, autoregressive framework for visual language tasks. It shows that high-quality visual understanding and generation can be achieved without relying on separate modules or complex pipelines. The Unified Vision Tower, with its contrastive learning and RQ, offers a valuable approach to handling discrete visual tokens. The research highlights the importance of careful training strategies and high-quality data, even with relatively smaller data sets. This work provides a strong foundation for future research in unified multimodal models.
Thank you for this insightful discussion.